Okay, well, welcome everyone to this meeting of the Virtual IMS User Group. Thank you for joining us today. I'm Trevor Eddles. I'm CEO of ITechEd Limited. We're a mainframe consultancy, analysis and technical authoring organisation. We're responsible for the content on the Virtual IMS website and in the newsletters. And if you haven't been on our website, you can find it at iteched.com/virtual IMS. And we also look after the Virtual Kicks user group as well. So first of all, let's just run through the agenda for this meeting. As usual, most of the meeting will be taken up with a presentation, and today our guest presenter is Karen N. Tischer, DBA, IMS, Education and Consulting, Instructor Consultant, and her talk will give us an overview of FastPath DEDBs. A copy of the slides from this presentation will be on the website later today. And by the way, if you've missed any of our previous meetings, you can download copies of those presentations from our website, and you can listen again to the whole sessions. There's links on our resources page. Following Karen's presentation and any questions you have for her, we'll move on to the latest IMS news and the latest IMS related articles. Feedback requests is there to remind me to ask you for your feedback about this virtual meeting. And then I'll give you the dates and times of the next couple of virtual meetings. So that's the plan for this meeting. I'm anticipating that it'll last around an hour. Anyway, as I just said, today's presentation is from Karen Tischer. Karen says she joined IBM in 19-something. She's not telling which year. And she worked as a systems engineer, then instructor, course developer for IMS. She left IBM 28 years ago and has been an independent instructor for companies providing both IBM training as well as courseware she and her partner developed. She specializes in IMS database design, implementation, performance and tuning, IMS DC, performance and tuning, IMS data sharing, IMS DBRC, IMS backup and recovery, IMS operations, IMS programming, that's database and data communications, and IMS FastPath, DEDB, MSDB, EMH. Her mission is to try to ensure that companies have the appropriate skill levels to maintain and advance their IMS systems into the future. And she says, long live IMS. So Karen, I'd like to thank you very much for being with us today. And what I'd like to do now is pass control of the meeting over to you. So let me stop sharing.
Thanks, Trevor.
Okay, let me just, you should see your presenter.
It says I'm the presenter.
Okay, so you can show your slides.
Okay. Good morning, good afternoon, good evening, and maybe good night. I don't know where you are. I see a long list of names from possibly around the earth. So there's a lot about FastPath DEDBs that we could talk about, but this is just going to be a very high level. Please feel free to ask questions. I guess, Trevor, we put the questions in the Q&A chat, and then Trevor will interrupt me.
Yeah, if they can put it in the chat or the Q&A, there's two choices on this, so whichever, I'll try and pick them up while Karen's speaking.
And I put the Roadrunner, this is a Roadrunner for those of you who don't know the birds of North America. It represents New Mexico. It's New Mexico's state bird, and it's very fast. Maybe you've seen cartoons with the Roadrunner outrunning the coyote. Anyway, FastPath is like the Roadrunner, and the coyote is like full function and HellDB. That's why I picked the Roadrunner. It's fast. I wrote an abstract So I can read this to you. But let me just paraphrase. Data entry databases came into existence before HALDB and gave us the ability to have large databases, high availability, because we partition the databases into areas. In HALDB, we call them partitions, but in FastPath, we call them areas. And that gives us large database, high availability, as we'll see as we move along. We have online reorganization and recovery built in. We have a feature called fast data collection, as well as some other features. But you can find FastPath in a lot of industries. First designed for the banking industry, so you'll see it in financial institutions. Package shipping and tracking, airline scheduling and reservations, manufacturing, telephone companies, among others. So, do you use FastPath? What is your industry? Why do you use FastPath? So let's see why they're so great. I'm very partial to FastPath. It's my #1 database. So our topics are overview, characteristics, unique features, followed by a summary. In an overview way, FastPath was delivered. Let me activate my pen because I can't talk without writing. So delivered with a database manager, available to online systems only, which means DBDC and a CICS DB control configuration. And they're designed specifically to provide high availability, large database, high volume, and high speed processing. The characteristics, they are HDAM-like. In other words, we randomize the root key to a root anchor point within an area. Partitioning can be done up to 9,999. Now I have an asterisk here, but I forgot the note. So the asterisk says there's an APAR that gives us that 9,999 capability, and that APAR number is PH 12671. And that's available as of IMS version 15.2. Okay. Prior to that, we were limited to 2048, and many years ago, I don't need to go into the history, we had way fewer because nobody thought that we'd need them. In any event, each area is supported by a single area data set, which is VSAM ESDS, maximum 4 gigabytes. And you might think, well, that's not a lot. But each area, 9,999 of them at 4 gigabytes, gives you a very large database. Access to the areas is different from regular VSAM processing because we wanted FastPath to be fast. We're using a capability of VSAM called the Media Manager. And the Media Manager has some requirements, one of which is your area data set must be pre-formatted before it's used, and you are not allowed to have any data set extensions after you have pre-formatted the data set. And you say to yourself, well, what if I run out of space? More later. Stay tuned. Almost all the utilities run online, and they run at the area level, and that's what gives us high availability. Commands also operate at the area level. So I can take an area away from the system, do whatever I need to do with it, reintroduce it to the system, and leave the other 9,998 areas available for processing. Okay. There is a restriction. You can have no logical relationships. Personally, I think that's a good thing. Logical relationships can really get messy. And it has some unique features, which we'll talk about along the way. Here's a list of the unique features that we're going to address, and I'm going to address them in this order. We're going to start with system functions, even though that doesn't pertain to the DEDB itself. When I talk about some of the other unique features, these system functions become very important. So from a FastPath point of view, we have special buffering. We have unique locking. We do logging differently from full function. And we do DASD updates, hardening the updates to DASD in a different way than we do for full function. The hierarchic structure is slightly different from full function. We store database records in a very strange way. We'll briefly stop by randomizing to give you an idea of what needs to be done in that area. And then we'll look at one of the big special features, sequential dependence, which was, as you'll see, directly relates to the name data entry database. So stay tuned. We have some special pointers developed by the Japan banking system called subset pointers. We can duplicate our data sets. This was necessary back in the days when we had DASD that was not nearly as reliable as today. 2314s, 2319s, 3330s, 3380s, numbers that you probably never heard before. We have something called high-speed sequential processing to allow batch message processing programs to move at a very quick speed when processing sequentially through the data. We have a virtual storage option that allows us to load data into memory or into a coupling facility structure, depending on how we are sharing the DEDB. And then we'll stop by and look at the utilities that run online that come with FastPath. So we'll start with the system functions. This is buffering. First of all, we have multiple buffer pools in 64-bit storage. Okay. These buffer pools are dynamically allocated to be the appropriate size based on the CI size of the area that you're opening. So we do a defined cluster, we specify a CI size of 12K. We're going to have in this big orange pool over here some 12K buffers dynamically allocated, and then the buffers are self-adjusting based on application access to that particular 12K set. Okay. Something completely different from full function is that each scheduled PSB, that can be a dependent region in IMS or a thread coming in from CICS, gets its own buffers, which it doesn't share with anybody else. So that's completely different buffering from full function, which has a big pool and everybody who needs 12K buffers can use that big 12K buffer pool. No, What's mine is mine, and what's yours is yours. I can't see what's in your buffers. You can't see what's in my buffers. So the illustration on the right here shows that I have a BMP running. It has a green set of buffers. I have a message processing program running with a purple set, an interactive fast path running with a blue set, and a Kix thread using the gray set. Okay. Now I have little acronyms in here: NBA, OBA, FPBuff, and FPBuff. NBA stands for normal buffer allocation. So I should be able to finish a single sync interval of processing using the NBA set of buffers, but just in case I can't, I have an overflow set. Overflow buffer allocation that I can use. If I exhaust all the buffers that were allocated to my dependent region, these are allocated to each thread, my program ends and all the work that it's done is thrown away. So this is on the JCL that starts each dependent region. And for CICS, the parameters are FPBuff and FPBuff, and that's in the CICS I can't think of the name of it, table that tells us how CICS is going to connect to IMS. Okay. There's no buffer look aside, which means, you know, if I want something over here that's in the purple pool, I can't see it. I have to wait. And I think I have an illustration coming up on that. Okay. Then at the very top of this picture, it doesn't matter where these buffers are, I just put them anywhere. We have some special buffers for collecting sequential dependence. Remember, I mentioned sequential dependence on the previous page. This is like a big bucket, and at commit time, if these applications have inserted sequential dependence, they're moved into the current sequential dependent buffer. They are not written out to DASD. We'll have a picture on that coming up. So the whole idea is fast data collection here. And then this gets hardened to DASD at a later time when the buffer is full. All right, now, since we have data in buffers, the data is locked, and locking is done by FastPass Lock Manager, which is a very simple lock manager. Locks are based on whatever the processing option is in your PCB. And I think most applications always say procopt equals A, whether they need it or not. They could copy a PSB and okay, everything looks good. And so if you have a procopt of A, everything is locked exclusively for your application while you are using it. So if we just look at the BMP buffer pool over here on the right, we see that we have a modified buffer with an exclusive lock. Unmodified also has an exclusive lock because procopt equals A. So modified, unmodified, mod, unmodified, mod, all exclusive locks. We could also have a read with integrity lock. That's a procopt equals G. Or we could have no lock at all, which is a procopt GO, one of the GO options. Okay. Now, what happens in FastPath if you have a deadlock? Well, the FastPath lock manager doesn't know. Everybody's just waiting. And so it says, I don't know, maybe there's a deadlock. We always have a partner. Probably in your installation, it will be the IRLM if that's the lock manager you're using for IMS. Otherwise, it would be program isolation. So the lock manager, FastPath, will ask IRLM, is there a deadlock? And IRLM is responsible for resolving the deadlock, figuring out which application should be victim. Here's a picture of 3 scheduled threads running. Left to right, we have an exclusive lock for MPR1 for the data in CI number 5, which is in its buffers. And going left to right, an exclusive lock for BMP2 has CI7 in its buffer, and CICS has an exclusive lock on CI number 9 in its buffer pool. So when MPR1 wants to acquire data in CI7, it waits. BMP2 is interested in some data in CI5, it has to wait. These two are deadlocked. So IRLM will be tapped on the shoulder and say, these guys are waiting. I don't know if they're waiting on each other. And the victim will be picked. And it's usually the shortest running unit of work or unit of recovery, whatever your preferred terminology is. So MPR1 will be pseudo abended and will reprocess immediately. As it pseudo abends, this lock is released, this guy gets the lock and goes on and finishes processing.
Karen, I've got a quick question.
Yeah.
It's from Mike Broweller. He says, if each MP has its own data buffers, does that mean those records are unavailable to other regions until they're hardened? Oh, no, he just said, never mind. Sorry, he must have answered that with your...
That's correct.
Yeah.
So
Thanks.
if I pseudo abend MPR1, that means the lock is released on this, and BMP comes out of the wait state and now BMP gets the exclusive lock on this and has this in its buffer pool. Meanwhile, MPR1 starts up again and it wants this. Because there's an exclusive lock on it, we now have to wait for the BMP to reach a checkpoint to release that lock. Okay. So this is something interesting here that will come into play when we look at the way the records are stored in the DEDB, right? If I have a database record in here, record 3000, I want all of the dependents to be in here, but maybe some of the dependents are over here, and that's what's causing this problem. So it's part of the design. So very difficult. I don't want to get too deep into this. Okay, and then CICS is over here. It has a transaction that is scheduled to thread. It's using the data in CI number 9, which is exclusively locked for CICS. And then the thread wants some data in BMP's CI7. So we're waiting over here in CICS. So the locks are bigger. The locks are on the control interval. They're not on the record. They're not on the segment. So whatever is in the CI is yours to use until you commit. So that would be the next thought. How does commit work in FastPath? So here's my BMP down here. I'll direct your eye. It does a commit. So it has a checkpoint call, CHK, whatever, KB, and it commits. The first thing we're going to do is we're going to release the locks on the unmodified CIs. They're not modified. I don't need to hold those locks anymore. So at commit, we release these guys. The next thing we do, number 2, is create the log record and move the log records for the CIs, and move those log records into the olds buffer, which is in ECSA. Okay, so here's the set of 6 modifications. We don't log the whole CI, we just log the data in the CI that has changed. So that's a good thing. So that's called logical logging. We build the after images, move into the olds buffer, and then if there is for some reason an append, there's no backout needed because all the updates are not written out to DASD yet. We don't do that during commit. Full function, the application has to do the logical logging, wait for the log records to be written to DASD, then we release the locks, and then the database is updated, and then the application can resume processing. We don't do physical updating during commit. We want to be fast. We do it after physical logging occurs, but the application is free to resume processing as soon as logical logging and physical logging occur. So we'll look at physical logging on the next page. So now my BMP waits until the log records are written to DASD. Physical logging occurs most of the time when the olds buffer is full. There are some exceptions. So the faster your IMS system is running, the faster this olds buffer fills up and gets written out to the olds. So when the olds buffer is full, I write it out to the online log dataset. The BMP then passes the modified buffers to a function in IMS called output thread. Here it is, number 2, author. It's a parameter in the startup of your IMS system. How many output threads do you want available for writing these updates out to DASD? So I've passed my old buffers over here to output thread. I'm now ready. I resume processing over here, and I start getting a new set of NBA and OBA for my next unit of recovery. Meanwhile, these guys still haven't been written out to DASD. That's okay. They're on the log. Okay, so I can always do recover. Output thread now is running asynchronously. It's taking those and writing them out to my DEDBs while my BMP has resumed processing with a new set of buffers. As soon as output thread finishes updating the databases, it releases the locks. Okay. Now, one of the other things that makes FastPath fast is that output thread cheats. It uses something called SRB processing. If you know anything about ZOS, we should be using a TCB, a task control block to do this output. FastPath uses SRB, System Request Block, which is a higher priority activity in the ZOS system. So these things get smashed out to DASD very quickly just because FastPath is cheating. Not everyone is allowed to do this. Okay. So my second unit of recovery is running over here in the BMP while Other is writing out to DASD. Life is good. So when output thread finishes writing out each modified CI, we release the locks and then return that buffer to the buffer pool so that there's buffers available for anyone else who might need them. So that's basically systems functions, just as a background. Let's see, how am I doing on time here? Now, hierarchic structure, and I just want to explain a little bit. In the beginning, over here on the left, anyone recognize what that is? That is a data entry room. And we have a lot of people sitting in the data entry room. Oh, good. We have men and women in this picture. Isn't that nice? And they're sitting at something called a key punch. And these folks are punching data into an 80-character card. At some point, the cards are collected, really a card. The cards are collected. We put some JCL in front of the cards. We put the JCL and the cards in a machine called a card reader. The program starts up, it reads a card, posts the account. Read the next card, post the account. Read the next card, post the account. Okay. Well, the idea is to trade in now the key punch and cards for an online transaction. Now these people are sitting in front of a green screen. They invoke the transaction. They enter the requested data. For example, what is the account number? What is the transaction type? You know, in a bank, what are the transaction types? For me, it's mostly withdraw. But you can have withdrawal, deposit, transfer. I don't know what else, but you know, there were other things. Transaction type, amount. Okay. So now we enter the account number. We put in the transaction type and the amount, and that program creates an insert to the database. So under the appropriate account number of what the transaction type and the amount is. And then we loop around and we get the next card's worth of data, do a get unique on account number, insert a sequential dependent with a transaction type and the amount in it, and so forth. That's why this is called a data entry database. At some point, rather than collecting cards, we run an online utility that extracts these sequential dependents to a sequential file, and that sequential file is then probably fed to a BMP that reads a record, posts the account, reads a record, posts the account, read a record, posts the account, read a record, posts the account. Okay. So this is the first example of environmental a database. We're no longer using cards that were made out of trees. Okay, so just to get a history behind the name. The current structure of a DEDB looks something like this. We have the root segment, and then on the leftmost segment at level 2 is optionally a sequential dependent. That's why it's in brackets. You can have up to 15 hierarchic levels with 127 segment types instead of the 255 for full function. The S-step is optional. All segments are stored on DASD. They carry the LL field. You can define them as fixed lengths to make life easier for your applications. Okay. The pointers that are supported are physical twin forward, physical child first and last. I don't know why I have this here. Guess I fell asleep at the wheel. And then new pointer, sequential physical child first and sequential physical twin forward. So those come out of here. SPCF, SPTF. Okay. Multiple positioning is the default for our PSBs. So you don't have to specify POS equals M in the PCB to get multiple positioning. You always have it with FastPath. My hierarchic structure in green at the top can be rearranged left to right by the PSB in purple structure on the bottom. So that allows the application program to process account payment path, account billing fees path, account audit path. They can move back and forth on those paths under the account segment without any problem at all. And why do we do that? Because the application wants to see payment first, and it wants to see the billing and fees, and then it wants to see the audit segment. So if you didn't have multiple positioning, you'd have to do random calls all the time down this path and that path and then this path and then over here. So multiple positioning gives applications a great advantage on being able to move left and right under the root. All right, now you have to store the data somewhere. Here's an area, and it's area data set, and it must be formatted. So when it's formatted, it looks like the can on the left. The formatting is done based on what you've specified in your area macro. There are a couple of weird things here. One is a unit of work, and one is a root, and the CI size that you're going to use for this data set, and it must match the vSAM CI size in your defined cluster down here. So a unit of work is a user-defined set of CIs. For example, in this column, I want 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And I want 2 of them set aside, the last 2, for special use. So the first 8 CIs are called base, and each one of these has one and only one wrap, however you spell, one wrap each. So I randomize into those CIs, 1 through 8, in a unit of work. Stay tuned for the next page. And I try to load my entire database record in the CI that's in the base section. If I have too much data, then I use this section down here, which is called Dependent Overflow. So I have a little overflow down here, and then if I run out of room in CIs 9 and 10, I need to extend this unit of work, and I do that by grabbing space out of 2 units of work set aside. These are the orange ones, called the independent overflow part, abbreviated IOVF. Okay. And you say, well, that's really weird. And it is really weird. But the whole idea behind this structure is to support online reorganization. When I do online reorganization, I reorganize 1 unit of work at a time. I don't want data spread all over the place. I want to have just a little bit of data to reorganize. I'm going to lock out 10 CIs. I'm going to unload them into memory and reload them back into this unit of work. Okay. To neaten everything up. Okay. So we have the section called the root addressable part. That stores roots and direct dependence. We have the section called in orange the independent overflow part. It's used for data set extension purposes, but we're not extending the data set, we're extending the unit of work. The records that go into this unit of work are really big and they need a lot of extra space. We're going to grab these and add them to that unit of work. We have something that's no longer used but still there, a reorganization unit of work. How big is it? In this case, it's 10 CIs in size. Not very big. And then if you are collecting sequential dependence under your account numbers that belong to this DEDB, they get collected in the pink part here. They are only stored here. So for Karen, who might be here, if I did a withdrawal, my sequential dependent might be stored here. And then later I did another withdrawal and it might be stored over here. So we'll see how this all works without hopefully too much in-depth discussion. So a unit of work is like a mini HDAM database. Here's an example. We have a root K, which randomized to wrap 7, and I'm storing the root and as many dependents as will fit in the CI. And I ran out of space in the CI, so I come down here into a dependent overflow CI and store the remainder of root K. So something in wrap 7 CI points down here to the DOVF CI. Root N comes along, goes into wrap 4, load as many dependents. It's too big. We continue loading down in DOVF. So it's continued down in the dependent overflow. And then T comes along, and just because it's randomized, it randomizes to the same wrap as K. So now I have a synonym. I go to wrap 7, there's no room there. I come down and I store the root and the dependents, as many as will fit in the remainder of the dependent overflow. But I had more for T to store, so I go over now to IOVF and I get a CI out of there and store the rest of the record. So I have basically extended the unit of work. Okay. Now we use a randomizer, and the recommended randomizer that comes with IMS is DFS HDC 40. It's not DFS. DF HDC 44. Just so used to. And it's a one-stage randomizer, but we want all randomizers to be two-stage. We want them to first pick the area that the data goes into and then randomize to a wrap within that area. So you could randomize, you could have your areas set up by branch office or by ATM number or time zone or division, account number, vehicle model, area code, zip code, employee number, other. In this case, we're using an employee number, and we have some way of determining that employee number 670159 goes into area 2. And so once I've picked the area, then I randomize, go through the randomizing routine to pick a root anchor point. And so 670159 always goes into area 2. Okay, we don't have a key range option. You have to have a two-stage that picks the area first. So you modify this routine. Having a two-stage gives me the advantage of, if I want to unload and reload this and make the data set larger, I don't have to unload and reload anything that follows it. Or if I want to change the characteristics of this area, its unit of work structure, its whatever. Okay. Here's a little bit about sequential dependence. The following threads are inserting sequential dependence into NBA buffers. Remember, NBA, normal buffer allocation, are owned by the thread. Okay. So I have a bunch of NBAs in gray across the bottom, and I have MPR1, 2, BMP3, BMP4, thread 5, and thread 6. They're all collecting sequential dependence, all in their NBA buffers. So when the first one of these commits, I take the contents of their buffer and copy that into the current sequential dependent buffer. Current sequential dependent buffer. Okay? No IO. Second commit, root 66. Third commit by thread 5, root 1, S-step. Fourth commit, root 10, S-step. Fifth commit, root 66, S-step. So that's all that happens during commit time. Okay? They're moved into, well, they get logged, but they get moved into the current sequential dependent buffer. And I don't write this buffer out to the data set until it's completely full. So if you were doing this as a non-sequential dependent, when I did a commit, I would have to do IO, 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 IO. I don't want to do that. I want to be fast. Collection. That's the whole point of this. Where do you see this? Posting credit card charges. Collecting the data to be posted to credit cards. And probably some other things that you could let me know about later if we have time. So the buffer fills up in this picture. Okay. And it gets written out to the first available space in the sequential dependent part. And it remains there until we extract them using the scan online utility. So the scan online utility has some controls that it uses that are stored in the data set itself that indicate where the logical beginning is and where the logical end is of the sequential dependence I want to scan. So let's say logical beginning, logical end. I scan these, okay? And then I remove them with a delete online utility, and all that really does is reset the logical beginning to point right here. And I start collecting from here on. And I use this part of the data set in a wraparound fashion. So I keep going. As long as things have been deleted, I can overlay them in the sequential dependent part. Okay. It's a sequential data set that's used in a wraparound fashion, stored in a direct access data set, a VSAM ESDS. Okay. All right, next special feature is subset pointers. I have an example of why we have them. We can do a get unique to the root. So we're positioned on there. This is our parent. And then I can do a get next for the direct dependent using a command code that says read pointer 3. So I come in here, oops, and I get this segment. And that comes back to my program. And I'm going to be processing this. Meanwhile, I said move pointer 3 to point to the next one on the twin chain. Okay. Needs to be specified in the DBD on the SegM. It needs to be specified in the PSB on the SendSeg. This application can use subset pointer 1 for reading only, 3 for updating. So if you're going to move pointer, you need to specify update. Things the program can do: set conditionally, unconditionally, or set conditionally. Move the pointer, zero out the pointer. Use the pointer to get, insert, and delete. Read pointer 1. Now, why is this a cool thing to have? Well, if you've already processed everything up to, but not beyond this segment, do you really want to say, I need to find this guy the old-fashioned way? You come down here, you twin forward. This could be a lot of I/O till you get out here to find the one you want. Okay. So it reduces I/O, gives you kind of direct access to the starting point where you need to resume processing. Okay. You could divide this up into, if you're in the banking business, I think of this as statements starting with for the last quarter. But let's just say January. January is the beginning. February, March, April. Okay. So it requires two things: database design and application design, and a definition for the application programmers to know which pointer is used for which purpose. Multiple area data sets were introduced because of DESD reliability years ago, but they do give us an advantage of being able to do online recovery. Okay. So when I go after data, I read from any of the 3 data sets. I have 21, 22, and 23. They all have identical data. I then update the CI that I just read. I commit the update. Now I'm going to write to all the data sets. to update the data on these guys, but when I try to write to 123, I run into an IO error. So there's an error queue element that's created saying you cannot get the data out of 123 anymore. So if somebody wants to read the data, they can still get it. It's okay here and it's okay there. Very handy back in the 2319 3330 days. So you can have up to 10 multiple area data sets. Seven, sorry, up to 7. Here's an example of online recovery. I have an error on 121. I have an error on 1228. And so I know that, and I run the create utility. It's going to read from 121 until it hits this error, and then it'll switch to, hang on, 122. Until it hits the next error. Meanwhile, I am updating this data set. I lost my mute button, I'm sorry. So I'm still doing read any, but I'm doing write specific out to this data set to create a nice clean data set. And at the end, that 8 area data set is marked as available for use by online.
So I've got a question for you. It says when EQE for ADS 123 will be fixed. So when will it be fixed? Is that what you're just saying now at the end?
Oh, no, that's, maybe I should have changed this. I'm using just these 2 data sets as my production data set in the next picture.
Right.
Right. So these are the only data sets that I have available online. These are both available.
Okay. Yes.
This one's unavailable. I've done a delete define cluster, and in DBRC, I've marked it as unavailable for online processing. Okay.
Okay, thank you.
Yeah, bad picture. Sorry about that. All right, next special feature is high-speed sequential processing, where BMP has a processing option of H. You can turn off high-speed sequential processing with a controlled data set input to the BMP that says no read ahead. But the whole idea is to quickly process this area. So we're going to use high-speed sequential processing, regardless of what the other processing options are, A, G, you know, I, R, D, whatever. You always get an exclusive lock, and it's on the unit of work. And we get, by default, starting this, 3 sets of buffers. And we're going to load these buffers. And if we're running really fast, we can acquire up to 6 sets of buffers to be preloading the unit of work CIs that are being processed. Okay. So I'm currently processing this CI. This one was the previous one processing. It's not waiting too long for logging and output thread processing, because if I've been doing updates, a physical logging is triggered immediately and output thread kicks off for these CIs that were locked exclusively. So I'm running through here processing this. When I cross a unit of work boundary, My program gets a status code to know to issue a commit. This becomes previous. I'm processing the next, and hopefully we're loading up the following 3 as well. The following 3 get conditional locks. If I can get the lock, get it, otherwise wait. And so a sequential processing BMP should be able to zoom through this area. If there are any CIs that are in IOVF, we still have to have NBA and OBA buffers. They don't get preloaded, they get loaded at reference time. VSO allows us to put data either in a ZOS 2 GB data space or out in a coupling facility structure. This would be a share level 0 or 1 database. This would be share level 2 or 3. Okay. You have to be registered with DBRC to do this. The idea is to reduce read memory IO because the data is in memory. It's moved from memory into your NBA buffer for application processing. It's moved from NBA back into the data space at commit time. It reduces write IO. Updates are logged. The data set and storage are updated. The data space and storage are updated, but the data set is not. The lock is released. So how fast is that? I log, I copy. Okay. Periodically, we do batch output, and that is at system checkpoint time. Whenever IMS takes a system checkpoint, we gather all the modified CIs from either the data space or the coupling facility structure, and we start loading them into the FastPath buffer pool and writing them out in a batch-like mode. This was designed as an alternative to a database called a main storage database. These are notes for VSO DBRC parms. I just include them for completeness. And then we have online utilities. They run in an FPU dependent region of your DB control or DBD system. They do increase data availability. You can run only 1 utility at a time against an area, and they use their own buffers, so they stay out of the FastPath buffer pool, which is a very nice thing. I mentioned scan and delete for the sequential dependence. For the multiple area data sets, we have a data set compare. We have an area data set create that works best if you have 2 copies of the data. We have high-speed reorganization. And finally, the newest online utility is Alter to allow you to dynamically change your DEDB specifications. So very quickly, you can alter the area, which includes changing your unit of work size, your CI size, and your root parameters, all things in the DBD. You can replace your randomizer. You can add areas to your DEDBs, along with being able to add segment compression exit routine. Also, if you're using IMS managed ACBs, we read and update from the IMS catalog. Alter DB, you can add new fields in places that were unmapped space. You can increase segment length. And all this is done without outage to anyone.
I've got another question for you,
Yeah.
which is going back a slide. They ask at what time it gets loaded in VSO.
It depends. If you say, back on page 27, preload, as IMS comes up, it's going to allocate the data space, it's going to connect to the structure in the coupling facility, and it's going to start loading a unit of work at a time at IMS startup time or at open time. So we've specified VSO. You can pre-open it. You can preload it. Okay. And there are some system parameters that will specify how you want the preload to work so it doesn't slow down the startup of your IMS system.
Okay, great. Thank you.
Okay. So just some documentation on the altered utility, what happened at each version. And that's it. So I think I went a little over. I apologize. I knew I had too many slides. Very high level. Come join me in a fast path class sometime. You'll have a great time.
No, oh, that was brilliant. Thank you very much. Has anyone got any questions? Type them into the chat. That would be good. Someone says, great presentation.
Thank you.
Yeah, someone else saying thank you, Karen. But yeah, can't see any questions.
Well, thank you for being here today. I appreciate it.
Yeah, lots of people saying thank you. Yeah, brilliant. Okay, well, if anyone does have any questions for Karen, if you email them to me, I can pass them on. Yeah, there's just hundreds of messages coming up saying thank you. So yeah, if you've got questions, send them to me. I'll pass them on, and I'm sure Karen will get back to you. So let me just make myself presenter, and we'll just quickly run through the last couple of my slides. Okay, yes. Oh, I must say, because we're a virtual user group, now you should be imagining that you're getting a virtual round of applause, Karen, because that was brilliant.
Thank you. I have applause taped so I can run it.
Oh, the experienced presenter, like. Okay, just going through my slides quickly then. I haven't got any news. If you know of anyone who's announced anything in the IMS world, can you get them to send them to me, please? In terms of articles, there was one from the very end of September. Want to significantly reduce application trace facility CPU usage. That was by Vitaly Mintz, and that's in the IMS part of the IBM Z and Linux One community page. There's a link to that on our website, of course. Feedback requests, I always put that in. If there's anything you think we can do to improve it, then just tell me. You can use our contact us page, or you can email me, and that's my email address, trevor@iteched.com. So as you can see, plan for the future, 7th of December, we've got Hayley Fung again talking about IMS and Ansible. That should be interesting. And then next year, 8th of February, we've got Dusty Rivers. You may think he works for GT Software, but of course the company changed its name a couple of months ago. So just a reminder, you can keep up to date with what's happening in the world of IMS and on the virtual IMS user group website by following us on Facebook and Twitter, or by joining the virtual IMS group on LinkedIn. The actual links are again on our website, so you don't need to try and write them down quickly. We like likes, so if you're on Facebook, like our page, and if you're tweeting or Instagramming or anything, then the hashtag to use is hashtag virtualims. Okay, well that's all for this meeting of the virtual IMS user group. Can I thank you all for attending? Thanks to Rocket Software and BMC Software, they're the people who sponsor our user group and make these meetings possible. And of course, I particularly want to thank Karen Tischer for today's brilliant presentation. So that's it. Thank you all very much for joining the meeting, and I look forward to seeing you on the 7th of December. So thank you all, and goodbye.
Bye. Thank you.